Continuing with section 4.1, let's move to example 7. Find the future value of $1,000 invested for 5 years at 4.5% compounded continuously. So here we're going to use, since it's continuously compounded interest, we're going to use A equals P e to the RT. So we need to choose the correct formula. Here, P is 1,000, R is 0.045, and T is 5. Remember, there's no value of n to substitute into this formula. So, substituting in now, A would be 1,000 times E to the R 0.045 times T, which is 5. When we multiply the numbers in the exponent, so we have 1,000 E, we obtain 0.225. And then we can use a calculator to compute the value, which, first of all, let me just show you what that is. It's going to be $1,252.32 to the nearest cent. We did a problem previous to this. Let's see. It was in example 6, $1,000 invested for 5 years at 4.5% compounded quarterly. And the amount we obtained, if you look back, was $1,250.75. So not even a $2 difference between compounding just 4 times a year and compounding continuously. So the increase in interest with continuously compounded interest is not necessarily much greater than compounding a certain number of times, a finite number of times per year, quarterly or monthly, something like that. But it is the highest amount of money we can earn under any compound interest scenario. Notice that in the formula for continuous compounding, the number e serves as the base of an exponential function. In particular, the function f of x equals e to the x is called the natural exponential function, or sometimes simply the exponential function, because it is really the most important exponential function. As you will discover if you continue into calculus, the base e is the most convenient base to work with when it comes to calculus applications. And this has something to do with the rate of change of the exponential function when the base is e. Since e is a positive constant not equal to 1, it can serve as the base of an exponential function, and the properties of f of x equals e to the x are similar to those of other exponential functions. Since e is approximately 2.72, e is between 2 and 3, so the graph of y equals e to the x lies between the graphs of y equals 2 to the x. It's steeper than y equals 2 to the x, and y equals 3 to the x. It's a little bit less steep than y equals 3 to the x, since e is a little bit less than 3. So you can see its graph shown. Again, the y-intercept is 0, 1, just like any other basic exponential function, and it is an increasing function with a graph rising from left to right. There is a more general formula involving the base e that we can use for applications that are similar to what we saw with continuously compounded interest. This is called the general exponential growth or decay model. It can be used for both growth applications and decay applications. If an initial quantity A0 grows or decays exponentially, the amount A at time t is A equals A0 e to the kt, where k is the relative rate of growth. if k is positive, or decay if k is negative. So k is a growth or decay constant. You'll have growth if k is a positive constant, and exponential decay if k is negative. I just want for you to note that the continuously compound, the formula for continuously compounded interest, a equals p e to the rt, is a specific case of this more general growth decay model. The p, the principal, plays the role of a0. The interest rate r plays the role of k. So it really is the same formula as the PERT formula, this new one that we're looking at. To conclude the notes, let's look at an application of the general growth model to population growth. The population of a town is expected to grow exponentially at an annual rate of 10% over the next 10 years. If the town's population is now 8,000, predict its population in 10 years to the nearest 1,000. So we're going to work with a equals a0, e to the kt power. Here the a0 is the initial population of this town, which is 8,000. K is the growth constant, and that's given as 10%, so we would write that as a decimal 0.10. It's kind of like an interest rate. And T is the time period that we're looking at, 10 years. So A is the future population, and that would be computed as 8,000. E to the K is 0.10 times T, which is 10. That is 8,000. E to the 0.1 times 10 is 1. And I just realized I failed to mention to you how we compute e to a power. I should mention that to you. I can't really demonstrate it, but I can show you, just show you the keys. Usually on your calculator, if you want to raise e to a power, you use the ln key. The key that says ln, we'll see ln represents the natural logarithmic function, and we'll talk more about logarithms in the next section. But above that key, you'll probably see something like e to the x. So what you're going to do to access that second function is to press your second or inverse key, then press ln. So to raise e to the first power, you would enter second ln and then the exponent of 1. And on most calculators, this is the way it's now done. You do second ln, you should see an e come up, maybe with a little exponent symbol, maybe not, and then maybe a set of parentheses, and you would just put your exponent in there and close the parentheses. This would be the same thing we would do in the previous example, example 7, where we were dealing with continuously compounded interest. So that's how that's done, and I'm sorry I forgot to mention that in the previous example. But we have to use that here, of course, as well. If we approximate this to the nearest 1,000, it's approximately 22,000. So the population after 10 years, according to this model, would be approximately 22,000. And you can see that here in the graph with t equal to 10. We're just talking about this point right here, and you can see that does appear to be about 22,000. What we are showing also in this graph is the a comparison of exponential growth to linear growth under the same conditions. If the population increased at a constant rate rather than at an increasing rate, then you'd have linear growth, and you'd see a straight line growth. You can see that through the first few years, the difference between linear and exponential growth is not very great. But as time increases, the difference becomes more significant as the exponential curve starts to curve away from the line. So exponential growth is, especially as time increases, is going to give you significantly more growth than what you would see with linear growth. That concludes the notes for section 4.1.